Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Welcome. You can let your shoulders relax and allow your breath to soften as you settle into this quiet moment. The world outside can wait. For now, there is only this gentle space and a slow exploration of a simple but profound question. What if reality, at its deepest level, is made of information? Not merely described by it, not simply measured by it, but composed of it. The way a story is composed of words, or a melody is composed of notes. This idea may sound unusual at first, even a little unreal, like something from speculative fiction. But it is not fiction. It is a serious line of thought, slowly developed, carefully debated, and cautiously explored by physicists, mathematicians, and philosophers who are trying to understand what the universe truly is. As you listen, you do not need to analyze or memorize or solve anything. You can simply drift through the ideas as if floating peacefully on a calm cosmic sea. When we look at the world around us, we tend to think first in terms of things: a stone, a tree, a planet, a person. We think of matter as the basic ingredient of existence, something solid with weight, with location, with physical presence. But when scientists began to examine matter more and more closely, they discovered that the solidity was only an appearance. Atoms were mostly empty space. Inside them, tiny particles moved according to mathematical rules, and those particles themselves were best described not as hard little beads, but as patterns, as relationships, as structured possibilities. So the question slowly emerged. If matter dissolves into patterns and relationships, then what exactly is fundamental? What lies beneath the surface of everything we see and touch and measure? Another way to think about this is to notice how deeply our lives depend on information. A book is just ink on paper or pixels on a screen. Its physical form matters, but only because it carries meaning. The story, the knowledge, the ideas are not the paper itself. They are patterns encoded and then decoded by a mind. Your body, too, is shaped by information. Inside every cell, molecules store instructions for building and maintaining you. Your experiences, your memories, your identity are supported by patterns of electrical and chemical activity inside the brain. In every direction we look, information is present. It shapes systems, guides processes, and connects events. And so a new suggestion has been made. Perhaps information is not just a description of reality. Perhaps it is reality. To explore this idea, we begin gently with something familiar, the simple act of noticing a pattern. When you hear a repeated rhythm, when you recognize a face, when you understand a sentence, your mind is picking out structure from a sea of possibilities. It is detecting information. Information in its most general sense is difference, a contrast between what might have been and what actually is, a signal against a background of uncertainty. It can be carried in sound, in light, in arrangement, in form. But the carrier is not the essence is the pattern. Just as a story can be told aloud or printed or typed or remembered, yet the story itself remains independent of the material that temporarily holds it. Human beings have always searched for the underlying nature of the world. Ancient thinkers looked for the basic substance out of which everything was formed: water, air, earth, fire. Later philosophers asked about space and time and existence itself. In the modern era, science added mathematics, measurement, and experiment. Layer by layer, our understanding deepened, and slowly a remarkable shift occurred. Reality began to look less like a collection of solid objects and more like a system governed by laws encoded in structure, equations describing movement, interaction, energy, and change, the language of information. It was as if the universe was not just something that exists, it was something that computes. Today, many researchers explore the idea that information may be even more fundamental than matter or energy or space or time. In this view, the universe is woven from relationships. States, values, probabilities, and constraints. Things do not just exist, they are specified. They carry and transform information. Light carries information from distant stars. Matter encodes information in its arrangement. Your senses collect information from the environment, and your conscious experience may itself be a complex flow of informational patterns integrated in the brain. When physicists study the smallest scales of nature, they discover that reality behaves as if it is built from discrete states, like yes or no, one or zero, true or false, tiny bits of specification. Even the limitations of what can be known about a system seem to obey laws related to information. It is as though the universe is constantly processing data, updating itself moment by moment, not with intention, not like a human-built computer, but simply as the natural unfolding of informational structure. This idea, sometimes called digital physics or informational ontology, does not claim certainty. Science rarely claims certainty. Instead, it offers carefully constructed models which attempt to describe the world as clearly as possible. And the informational perspective is one such model. It says, perhaps reality is not a collection of stuff. Perhaps reality is a vast network of distinctions, patterns organizing themselves into forms and behaviors, and what we call matter is one expression of those patterns. What we call energy is another. What we call space and time may themselves be products of deeper informational relationships. You may notice a gentle resemblance to the idea of code. A program defines behavior through symbolic rules. Change the code and the world described by it changes too. But here we speak carefully. We are not saying the universe is literally a programmed simulation. Rather, we are observing that the mathematics of information theory seems to describe physical reality with unusual depth. And so we allow the possibility that information is not just a metaphor, but a foundational element. Alongside this, there is another question. What role does the mind play? Your awareness is a receiver and interpreter of information. Light strikes your eyes, sound vibrates in your ears, touch signals travel along nerves. Your brain combines these signals into a coherent world, a world of colors, textures, memories, and meaning. In that sense, consciousness is inseparable from information. It is both shaped by it and engaged with it. Some thinkers wonder whether consciousness is simply an advanced informational process. Others suggest that consciousness reveals something fundamental about how information can be experienced. We do not need to decide here. We simply notice that information sits quietly at the center of both physics and psychology, a bridge between the external world and the inner one. As you rest with these ideas, you may notice how calm they can feel. There is no rush, no pressure, no demand for belief, just the simple invitation to imagine a universe not as a pile of objects, but as a flowing tapestry of distinctions and relations, where patterns form, evolve, combine, and dissolve, where complexity grows from simple rules, and where every star, every atom, every heartbeat is a part of one grand informational structure. The language of nature. This line of thought also brings a quiet humility, because if reality is made of information, then our understanding is always partial. We glimpse only fragments of the cosmic code. We build models and test them and refine them. But the totality remains vast and mysterious. And that mystery need not be frightening. It can be peaceful, a reminder that existence is deeper and more subtle than any single picture or theory. It is also reassuring to remember that the idea of informational reality is not intended to diminish the world. It does not say that life is unreal or that experience is an illusion. Instead, it suggests that meaning and pattern are built into the fabric of existence itself. That structure, not substance, is the truest description of what is, and that beauty and complexity arise naturally from the play of information across the cosmos. Imagine standing beneath a clear night sky. Countless stars glow softly across the darkness. Each one is a system of enormous energy, but it is also a system of information. Its mass, its temperature, its composition, its motion, all encoded in the light that travels across space to reach your eyes. The universe whispers data everywhere, and your mind quietly assembles it into a picture, a story of where you are and what surrounds you. In that sense, you are both a product of information and a participant in it, a node in the cosmic network. So as you rest here with steady breath and open curiosity, you may allow a gentle question to linger. If reality is made of information, what does that truly mean? How does information behave? How does it shape matter, energy, and the flow of time? And how do we as conscious beings fit into this vast web of structure? There is no need to hurry toward answers. For now it is enough to drift in the spaciousness of the question, to feel the calm of possibility, and to sense that the universe may be far more subtle and intricate than our everyday experience reveals. A quiet informational symphony, unfolding moment by moment, within and all around us. Imagine you are looking at a simple pattern, a row of lights, some of them on, some of them off. You glance once, and in that moment you can tell which lights are glowing and which are dark. You have gained a small amount of information. If all the lights were off, there would be nothing to distinguish, no pattern, no difference, very little information. If all the lights were on, again there would be no contrast. What makes a pattern informative is that some parts are different from others. This is one of the simplest and most powerful ways to think about information. Information is difference, difference that matters, difference that can make a change, a difference that makes a difference. A more mathematical way to say this is that information reduces uncertainty. Before you looked at the row of lights, you did not know which ones were on and which ones were off. There were many possibilities. When you look, you select one particular arrangement from all the possibilities. Your uncertainty shrinks. Information has been gained. This idea does not depend on lights. It works for any system. It might be letters in a word, bases in a strand of genetic material, energy levels in an atom, or the microscopic states of a physical gas. In every case, information measures how precisely a state is specified, how much uncertainty has been removed, how many alternatives have been ruled out. In the middle of the 20th century, a mathematician and engineer named Claude Shannon developed a formal theory of information. He was interested in a very practical question. How can messages be sent reliably over noisy channels? How much data can be transmitted through a cable or a radio link or a telephone line without error? To answer this, he needed a way to quantify information, not in terms of meaning, but in terms of uncertainty. He imagined a source that could produce different possible messages. Each message had some probability. The less likely a message was before it was received, the more surprising it would be, and the more information it would carry. From this simple foundation, he derived a measure of information that depends on probabilities. He showed how to compute the average information content of a source, how to compress messages into the smallest possible form, and how to understand the maximum capacity of a communication channel. All of this without caring whether the messages were words or images, commands or measurements. The content could be anything. The theory treated it as pure structure, as patterns of symbols, often abstracted as units that could take one of two values, on or off, yes or no, 1 or 0. These minimal units came to be called bits, short for binary digits. A bit is the tiniest possible distinction, a simple yes or no. But from many bits you can build complex messages, pictures, books, codes, entire libraries. Shannon's work revealed something profound. Information could be treated almost like a physical quantity. It could be measured, transformed, stored, erased, optimized, subject to constraints, and limited by deep mathematical laws. Now imagine looking at nature through this lens. An atom, with electrons that can occupy discrete energy levels. In many situations, these electrons could be in several states. Each possible state has a probability. To describe the atom fully, you need to specify which energy level is actually occupied. You need information, a molecule inside a living cell, its structure, its shape, its orientation, all encode information, a long chain of molecular units in genetic material. Each unit can be one of 4 types. Their sequence spells out instructions, a 20-letter alphabet of amino acids, a complete library of recipes for building proteins. Here information is not just abstract, it has consequences. Change a symbol, replace a unit, and the resulting protein may fold differently, behave differently. A tiny shift in informational pattern can cascade into a large change in function. In this way, living systems are built from informational codes. They read, copy, edit, and interpret these codes. They depend on the faithful transmission of patterns, across time, across generations, across networks of cells. Information is also present on cosmic scales. Consider a star, its mass, its chemical composition, its temperature, its age, its motion through the galaxy. All of these properties can be measured. All of them encode information. The spectrum of its light, the specific colors and intensities we receive, form a detailed signature. From this signature, astrophysicists can infer surface temperature, chemical abundances, surface gravity, even the speed at which the star is moving away or toward us. The star is a radiant source of information, carried by photons, streaming outward, spreading its physical state into the universe. When those photons reach our telescopes, they reduce uncertainty. What was once unknown becomes specified. Again, information is gained. Even more striking are black holes. Regions of space-time from which nothing, not even light, can escape. When matter falls into a black hole, we might imagine that information about its detailed state is lost, but careful analysis suggests otherwise. The surface area of the black hole's boundary, known as its event horizon, appears to be proportional to the maximum amount of information the black hole can contain. The information content, or entropy, does not scale with the volume, but with the area. This is such a surprising result that it has reshaped how physicists think about information and gravity. But even before we reach that deeper level, we can already see nature seems to keep track of possibilities. To every physical system, there is an associated set of possible microstates, configurations of parts, and the actual state. The one that is realized is one choice among that set. The description of which choice is information. At this point, it is natural to ask a careful question. How does information relate to more familiar quantities, like energy and matter? Are they separate, or are they intertwined? In classical physics, matter and energy were distinct. Matter had mass. Energy was something it could possess. Kinetic, potential, thermal. Relativity showed that mass and energy are deeply connected. Mass can be converted into energy. Energy can have an effective mass. In modern physics, matter fields, energy, and space-time geometry all interact. Information enters this picture in a more subtle way. Whenever matter occupies a particular arrangement, whenever energy takes specific values, there is information in that arrangement. The total information needed to describe a system depends on its possible states, on how finely we distinguish them, on what we know and what we do not know. In one sense, information is not a new substance. It does not float above matter and energy. Instead, it describes their configuration. In another sense, information is not arbitrary, because not every configuration is allowed. Physical laws restrict what can happen. They shape the space of possibilities, and thus they shape how information can be organized, how it can flow, how it can change. Thermodynamics provides a clear example. Consider a box filled with gas. We may know its temperature, its pressure, its volume, but we usually do not know the exact position and velocity of every molecule. There are many different microscopic arrangements that would all correspond to the same macroscopic description. The entropy of this gas captures how many microstates are compatible with the macrostate. More possible microstates. Higher entropy. From an informational perspective, entropy tells us how much information we lack. How many details about the precise configuration remain unspecified. If we suddenly measured every molecule's position and velocity, we would gain a huge amount of information and effectively reduce the entropy. In practice, we rarely do that. Instead, entropy tends to increase. As systems evolve, they move into states that can be realized in more ways, with more possible microstates. The precise initial conditions become spread out. Information about them becomes hidden. This is why, in an everyday sense, we say disorder increases. But from the viewpoint of information, we can say, the missing information about the details grows over time. One of the most striking links between information and physical law is the realization that erasing information has a necessary energy cost. Imagine a simple memory element. It can be in state 1 or state 0. If you want to reset it, to force it into one fixed state, regardless of its prior value, you must interact with it. You must couple it to some environment. During this process, at least a minimal amount of energy must be dissipated, usually as heat. This is not just a practical limitation, it is a fundamental one. It says that changing information, specifically forgetful changes, cannot be done without physical consequence. The act of erasing, of compressing many possibilities into a single outcome, writes a small signature into the surrounding world. This signature appears as an increase in entropy, and that increase must be compensated by energy flow. This principle ties together information theory, thermodynamics, and the microscopic physics of matter. It shows, in a precise way, that information and energy are connected, different faces of the same underlying structure. When physicists contemplate all of this, a pattern emerges. Information behaves lawfully, it can be quantified, its flow is constrained, its loss has cost. Its arrangement in microscopic states determines macroscopic behavior. In communication systems, in thermodynamic systems, in quantum systems, the same mathematical structures reappear. So some researchers have taken a bold step. They suggest perhaps information is not merely a convenient way for humans to talk about physics. Perhaps it is not just a description. Perhaps it is part of what the universe actually is. In this view, matter and energy are ways that information is instantiated. Space-time is a way that information about events is organized. Physical laws are rules that govern how information can change, and the unfolding of the cosmos, from one moment to the next, is an ongoing transformation of informational structure, not a story written from outside, but a natural process, as inherent to existence, as the passage of time. This perspective does not claim to be final. It is still developing, its details are debated, its implications are explored with care, yet it offers a unifying language, a way to connect. The structure of atoms, the behavior of gases, the dynamics of stars, the mysteries of black holes, and even the workings of the mind, under a common idea that difference, uncertainty, pattern, and their transformation are central to reality. As you rest with these thoughts, you can allow them to drift gently, like distant constellations. You do not need to hold them tightly. It is enough to sense that when physicists speak about information, they are not speaking only about data on a screen. They are speaking about the very way the universe distinguishes one possibility from another, the quiet logic by which reality selects its states, moment by moment, in an unending cosmic unfolding. When you think about information, it can be helpful to imagine layers. At the surface, you experience messages, a sentence spoken aloud, a sign on a screen, a pattern of notes in a melody. Beneath that surface, there is structure, letters, symbols, signals, and beneath that, there is the physical system that carries those signals. Vibrating air, electrical pulses, light moving through space. Information lives in the relation between these layers. It is not the paper, not the ink, not the sound. It is the arrangement, the pattern, the way one possibility is chosen from many. Physicists generalize this idea and apply it far beyond human communication. They look at atoms, tiny systems with allowed energy levels. An electron in an atom cannot have just any energy. It must occupy one of a set of quantized levels. If you do not yet know which level it is in, there is uncertainty, several possibilities. Once you measure it, one particular level is revealed. The uncertainty shrinks. Information is gained. The atom itself is a storage device. Its state encodes a tiny amount of information. In living systems, information takes on even more visible form. Inside each cell, long chains of molecules store instructions for building proteins. These chains use a small alphabet. Each position in the chain can be filled by one of 4 basic units. If you know the full sequence, you can predict which proteins can be built. If you do not, there is uncertainty. The sequence is information. A long chain containing thousands of units carries a vast number of possible combinations. Only one sequence is actually realized. That choice from all the possible sequences is an informational specification. Mutations are changes to the sequence, tiny edits to the information, sometimes trivial, sometimes profound. From an informational viewpoint, an organism is not only matter, it is matter arranged according to complex codes, codes that have been shaped by long history and that are constantly being copied, interpreted, and maintained. Language provides another clear example. The same physical sound, the same pattern of ink can mean different things in different languages. Meaning depends on shared rules, a system of distinctions, which combinations of symbols are allowed, which combinations are familiar, which sequences are interpreted as words, grammar, context. All of it forms an intricate web of informational structure. When you hear a sentence, you do not attend to the physics of sound waves. You attend to the pattern, the sequence. You decode information, and that information shapes your thoughts, your decisions, your memories. Once again, the physical medium is necessary, but the medium itself is not the message. The message is the pattern carried, the arrangement of possibilities into one specific realization. On cosmic scales, we see information encoded in starlight. When light is spread into a spectrum, its detailed pattern, bright lines, dark gaps, gradual slopes, reveals the composition of the emitting gas, the temperature, the density, the motion toward or away from us. Each photon, each packet of light, carries a little piece of information, not only about the star, but about the path it has taken. When that light reaches an instrument, when it is absorbed by a detector, the state of the detector changes. The prior uncertainty about the star's properties is reduced. We have learned something new. Here again, information is the reduction of uncertainty. Through the arrival of a structured signal, even the most extreme objects we know of, black holes, can be discussed in informational terms. When matter falls toward a black hole, the details of its internal configuration, the exact positions of its particles, the fine structure of its fields, seem to vanish behind the event horizon. From the outside, we can no longer see those details. And yet, the black hole's mass, its charge, its rotation, all contribute to the size and shape of its horizon. There is a strong connection between the surface area of this horizon and the maximum information content of the black hole. The greater the area, the more distinct microstates could be hidden behind it. This idea that the entropy of a black hole is proportional to its horizon area, not its volume, has deep implications. It suggests that nature somehow counts microstates, that the universe knows how many arrangements could correspond to a given macroscopic object, and that this counting is reflected in geometric quantities, such as area. It is as though information, at least in principle, is preserved and accounted for. Even in regions where our direct access to details is cut off. To make sense of all these phenomena, physicists extend the perspective introduced by Claude Shannon. They think of any physical system as capable of being in a variety of states. Each state has some probability. The more states are possible, the larger the uncertainty, the more information it would take to fully specify which state the system is in. Shannon's formula for information content, originally derived for communication sources, turns out to mirror another fundamental quantity, entropy. In statistical mechanics, entropy is defined in terms of the number of microscopic configurations, or microstates, that are consistent with the macroscopic variables we can observe. The more microstates, the higher the entropy. Shannon's measure and the statistical measure of entropy share the same mathematical form. This overlap is not an accident. It reveals that thermodynamic entropy, which tells us about heat and disorder, can also be interpreted as a measure of missing information about the system's precise details. You can imagine a gas in a container. You know its overall temperature, its pressure, its volume, but you do not know, and realistically cannot know, the exact positions and velocities of each molecule. There are an enormous number of possible detailed configurations. They all produce the same macroscopic values. Entropy is related to the logarithm of this number of microstates. From an informational standpoint, it tells you how many bits would be required to distinguish one microstate from another. If you wanted to fully specify the system, higher entropy, more missing information. This connection between entropy and information leads to subtle consequences. Suppose you try to decrease entropy, to compress possibilities, to place a system into a more ordered state. At some point, you must erase information. You are discarding distinctions, treating many prior states as equivalent. From the standpoint of information theory, that is a many-to-one map, from a variety of possible initial conditions to a single final condition. Such an operation, if carried out physically, has a minimum energy cost. Erasing one bit of information, resetting a simple memory cell, requires the dissipation of a certain tiny amount of energy as heat. This is not just a technological detail, it is fundamental. It tells us that information is anchored in the physical world. Changes in information, especially changes that throw away detail, cannot occur without affecting energy and entropy. This result is known as a principle that binds together computation, thermodynamics, and information theory. It underlies the understanding of how efficient physical computers can be, and it informs models of how any physical process that performs logical operations must behave. Even a simple particle in a double-well potential, behaving as a physical bit, is subject to this constraint. What emerges from all of this is a picture in which information, although abstract, is not detached from physical reality. Every time you store data, every time a system evolves from one macro state to another, every time heat flows, there is an informational story running in parallel. Microscopic states are rearranged, some distinctions are lost, others are created. Uncertainty grows or is reduced. The laws of physics impose boundaries on what is possible. They constrain how information can be organized, how much can be packed into a region, how fast it can be transmitted, how thoroughly it can be erased. This leads to a subtle shift in perspective. Traditionally, we might think of information as a secondary concept. We start with matter, with fields, with forces, and only later we describe those systems using information. But the more we examine, the more it becomes plausible. That information is not just a description. It may be an indispensable part of the ontology, the catalog of what is fundamentally real. If every physical state is also an informational state, if the evolution of the universe is simultaneously the evolution of informational structure, if energy costs, temperature changes, and entropy flows are all intimately linked to information, then perhaps it is useful, and maybe even necessary, to treat information as something basic, on par with matter and energy, rather than as an afterthought. If you adopt this view, then the question, is reality made of information, becomes more than a metaphor. It becomes a candidate answer to the search for fundamental ingredients. In the same family as saying, reality is made of fields, or of quantum states, or of space-time geometry, the informational picture, instead of focusing on substance, focuses on distinctions, on patterns and relations, on which configurations are allowed, how they transform, and how they can be known. At the same time, it is important to keep a calm sense of proportion. Physicists do not claim that we have already fully reduced the universe to bits. There are many open questions, many competing frameworks, many unresolved tensions. The informational perspective is one powerful lens. It organizes several domains of physics. It clarifies connections between thermodynamics, computation, and quantum theory. But it is not the final word. Its value, at least for now, is that it reveals that what we call reality is profoundly structured, and that this structure behaves in ways that can be captured by the mathematics of information, from the discrete states of atoms to the codes of living cells, from the signals in communication networks to the entropy of black holes. The same concept, information, silently connects them, acting as a shared language through which very different systems can be understood. As you rest with this, you might picture not a universe of solid blocks, but a universe of distinctions, layers upon layers of choices, yes or no, here or there. This configuration instead of that one, these microscopic possibilities, out of all the others, each layer, from the smallest scales to galaxies to thought, built on patterns, encoded, transformed, and conserved. In this gentle way, information ceases to be only something we store on devices. It becomes a way to describe what exists, and a hint that the fabric of reality may itself be deeply informational, from the tiniest bit to the vastness of the cosmos. Imagine shrinking your view of the world smaller and smaller, past the scale of cells, past the scale of molecules, down to the level where electrons and photons and other fundamental particles become the main actors. In this domain, the familiar rules of everyday experience begin to bend. Objects no longer have sharp positions and clear paths. Instead, they behave in ways that seem to belong more to information and possibility than to solid matter. In classical physics, if you know the position and velocity of a particle, you can in principle predict its future. Its path is well defined, its state can be fully specified. Quantum physics tells a different story. At very small scales, there is a fundamental limit to how precisely we can know certain pairs of quantities. Position and momentum, energy and time. This is sometimes called an uncertainty principle. It does not mean our instruments are clumsy. It does not mean we simply lack technology. It means that nature itself does not allow a state in which both quantities are sharply defined at once. The more precisely you pin down one, the more uncertain the other becomes. This is not just a statement about knowledge, it is a statement about what can exist. The quantum state of a particle does not assign a single definite position and a single definite momentum. It assigns a distribution of possibilities, a spread of potential values. To describe this, physicists use a mathematical object often called a wave function. It is not a wave in ordinary space, like ripples on water, but a wave-like entity in an abstract space of possibilities. For a particle's position, the wave function assigns an amplitude to every possible location. If you square the magnitude of this amplitude, you obtain something that behaves like a probability density. It tells you, if you perform a measurement of position, how likely you are to find the particle here or there. The same is true for other measurable quantities. The wave function encodes information not about what is, in a single definite sense, but about what could be observed and how likely each outcome is. It is a compact representation of potential measurement results, a kind of informational catalog of possibilities, waiting to be sampled. When you actually measure one of these quantities, something special happens. Before the measurement, the wave function may assign non-zero probabilities to many outcomes. After the measurement, you obtain one result, one specific position, or one specific energy. The probabilities for other outcomes do not materialize. The state of the system is updated. It becomes consistent with what was observed. In this way, measurement can be viewed as a process of information extraction. Before you interact with the system, you have incomplete information. The wave function represents this partial knowledge, along with the underlying limits imposed by quantum rules. When you perform a measurement, you reduce uncertainty, you gain information, but you also change the system. The act of gaining information and the evolution of the physical state cannot be cleanly separated. They are intertwined. And this intertwining is one of the most distinctive features of the quantum world. Another way to see the informational character of quantum states is to consider systems that are not in a single classical configuration, but in superpositions. A superposition is not the system being in two classical states at once. In a simple metaphor, it is more accurate to say the system is described by a wave function that combines contributions from several possibilities, each with its own amplitude. Until a measurement is made, we cannot say which classical result is real, only that the system behaves as though all of them contribute to its future behavior. In mathematical terms, the amplitudes interfere, reinforcing some outcomes, suppressing others. When we finally perform a measurement, the outcome we see is one sample, drawn according to the probabilities encoded in the wave function. The state then updates, reflecting the new information. In this sense, a quantum state is deeply informational. It is not a picture of small particles following tiny paths. It is a rule, a structured collection of numbers that allows you to compute probabilities and update them when data arrives. When quantum systems are not isolated but interact with their environment, the situation becomes richer. Consider a very small system, such as a molecule, surrounded by a large environment, such as a fluid or a solid, or even the radiation field. The small system can become entangled with many degrees of freedom in the surroundings. Their quantum states become correlated. Information about the small system is distributed, not localized anymore. When we trace over or ignore the detailed state of the environment, the small system appears to lose coherence. Instead of behaving like a single unified wave function, it looks more and more like a statistical mixture, a set of alternatives, each with some probability. This process is known as decoherence. It does not rely on conscious observation. It arises from the natural interaction between systems. As information about phases, the relative structure of amplitudes, leaks out into the environment, interference effects between different components of the superposition become practically impossible to observe. From an informational perspective, decoherence is the gradual broadcasting of which-way information. The environment, with many degrees of freedom, becomes a kind of witness, carrying records about the system's behavior to many places at once. The small system is no longer described by a pure state, but by an effective mixture, reflecting the information that has dispersed. Another hallmark of quantum reality is entanglement. Imagine two particles that have interacted, or that were created together in a correlated way. Their joint state cannot be described by specifying a separate wave function for each one. Instead, they share a combined state, in which the possible outcomes of measurements on one are correlated with possible outcomes on the other, even if they later move far apart. If you measure one particle, you gain information not only about it, but also about the other, instantly reducing the uncertainty about distant outcomes. This does not allow faster-than-light communication. The individual outcomes still appear random, but the correlations between them cannot be explained by any classical theory, in which the particles simply carry hidden labels. Established in advance, experiments, inspired by arguments due to John Bell, have tested these correlations over and over again. They show, again and again, that quantum entanglement is real. The statistics of measurement outcomes violate inequalities that any classical theory, with only local hidden variables, would obey. These results, together with many refinements, support the conclusion that quantum states contain a kind of non-classical information. Information that is not localized in one place, but shared among entangled systems, in a way that has no simple analog. In classical physics, from an informational standpoint, entangled systems are best thought of as a single, distributed object. The outcomes we see at separate locations are different views or partial readings of a unified informational structure. When we perform measurements, we carve out definite values from this structure, but the underlying correlations were already present, encoded in the shared state, not stored, like written labels, inside each particle, but residing in the joint description of the pair or of the larger collection. These insights have led to a new field, quantum information science. Instead of treating quantum effects as mere curiosities, this field embraces them as resources. Quantum bits, or qubits, are the basic units in this framework. A classical bit can be either 0 or 1. A qubit can exist in a superposition of the two, with complex amplitudes. A qubit state encodes more structure than a simple classical alternative, and multiple qubits can be entangled, forming states with correlations that cannot be factorized into simple, independent pieces. Quantum computation uses operations that act on qubits to manipulate this structure. Certain algorithms can exploit superposition and entanglement to perform specific tasks more efficiently than any known classical procedure, searching unstructured data, factoring large integers, simulating other quantum systems. These advantages are not magic. They arise because quantum computers process information in a space of possibilities much larger than the space used by classical bits. A register of many classical bits explores one configuration at a time. A register of qubits evolves according to rules that transform many amplitudes in parallel within a single wave function. The resulting interference patterns can enhance certain outcomes and suppress others in carefully controlled ways, producing computational speedups for specific problems. Quantum cryptography is another domain where informational aspects of quantum theory become central. Protocols where keys are encoded in quantum states can detect eavesdropping because any attempt to gain information about the key necessarily disturbs the state. This disturbance can be made visible to the legitimate parties again. The key point is that measurement and information gain are inseparable from physical change. One cannot quietly copy a completely unknown quantum state without leaving a trace. This is sometimes expressed as the impossibility of perfect cloning of arbitrary states, another uniquely quantum constraint on information processing. Taken together, all of these facts paint a consistent picture in the quantum world. Physical systems are not simply tiny objects carrying fixed properties. They are carriers and processors of information described by states that encode probabilities and correlations. The fundamental laws tell us how these states evolve, how they combine, how they decohere, and how they change when we obtain data from them. In this view, the essence of a quantum system is not its material substance, but its informational state, where it can be, what can be observed, how it is correlated with other systems, and how that structure changes over time. For many researchers, this strongly suggests that information is not an accidental feature of our descriptions, but a core ingredient of the physical world. The universe, at its smallest scales, behaves as if the fundamental currency is not solid bits of matter, but structured probability and correlation. and what we call matter appears as the stable patterns which emerge from these underlying informational rules. When we look closely, the world is less like a set of marbles and more like a constantly evolving quantum code, quietly computing its own future possibilities as it unfolds. Think of a simple experience. You drop a glass, it falls, shatters on the floor. You never see the shards leap back up, reassemble, and return to your hand. In the world of everyday life, time has a direction. There is a before and an after. Causes precede effects. Memories point backwards, not forwards. This one-way character of time is sometimes called the arrow of time. But if you look at the basic equations of microscopic physics, many of them run perfectly well in either direction. If you reverse the sign of time in those equations, the mathematical form often stays the same. So where does this sense of direction come from? Why does time feel as if it flows from past to future? And why are broken glasses common, while unbreaking glasses are not? A powerful part of the answer comes from entropy and from the way information is organized. Consider the glass in your hand. It is a fairly ordered object. Its pieces are aligned, its atoms arranged in a structured lattice. When it falls and shatters, all those pieces, spread out, the number of ways those fragments can be arranged on the floor is enormous. Each different configuration of tiny positions and angles would still look to you like a broken glass from far away. But the number of configurations that look like an intact glass in your hand is much smaller. Those atoms and pieces must be arranged in a very special way. So we can say there are far more disordered states than ordered states, and a physical system left to evolve without special constraints will almost always move from one of the relatively rare ordered configurations into one of the overwhelmingly many disordered ones. This natural tendency of physical systems to move into states that can be realized in more microscopic ways is what we call an increase in entropy. Entropy, in statistical mechanics, measures how many microscopic arrangements correspond to the same macroscopic appearance. The more microstates, the higher the entropy. From an informational standpoint, entropy also measures how much detail about the exact microstate you are missing if there are many ways for the system to be which all look the same. At the coarse level, then you lack information about which specific microstate is actually realized. More entropy means more missing information. Imagine that, at the beginning, you know the exact positions and velocities of all the atoms in the glass and in the surrounding air. In principle, you could reverse their motion and reconstruct the past. But in practice, any small uncertainty, any tiny error in that specification grows rapidly as the system evolves. Molecules collide, patterns of motion spread and mix, information about the initial state becomes distributed across more and more degrees of freedom, effectively hidden from any simple measurement. This spreading of information makes it impossible to put the system back into precisely the same state without an unrealistically detailed intervention. So when we look at everyday processes, we see entropy increase, information about detailed beginnings being lost into unobservable correlations. The arrow of time is the arrow of increasing entropy, the arrow of information becoming harder and harder to recover. This picture also helps explain why we remember the past, but not the future. A memory is a record, a physical system that contains information about another system. At some earlier time, your brain, the molecules in a photograph, the bits in a digital file, all of these are arrangements of matter that correlate with what happened before. When an event occurs, some of the information about it is copied into many places. Light reflects from objects, leaves traces on film or on sensors. Sound waves cause patterns of vibration that may be recorded. Your nervous system changes its internal state in ways that depend on what you experienced, creating a biological record. These records all point in the same temporal direction, from earlier events to later traces. We do not find records of future events because those events have not yet been selected from the space of possibilities. The information about them does not yet exist to be copied into our brains or our instruments. The flow of entropy from low to high creates an asymmetry in how information is laid down in the universe. Past events leave trails, future events do not. So the structure of information itself favors one direction as the direction we call past to future. You can picture time in this view as the gradual rearrangement of information at early stages. The universe may be in a relatively low entropy state, with information concentrated in simple patterns. As it evolves, matter clumps, structures form, stars ignite, planets cool, and entropy increases. Information about the exact initial conditions becomes more and more diffused, hidden in subtle correlations. At the same time, new structures appear: galaxies, stars, molecules, living organisms. These structures are pockets where information is locally organized. Even as the total entropy of the whole continues to rise, from this perspective, the passage of time is not just a parameter in equations. It is the story of information redistributing, of correlations spreading, of rare low-entropy configurations, slowly giving way to more typical high-entropy ones. The unfolding of the universe is the unfolding of informational structure. Living systems offer a particularly vivid example of how entropy and information interact. A living cell maintains a high degree of order. Its molecules are arranged in precise patterns. Its membranes maintain concentration gradients. Its internal processes are regulated. These states are highly specific. They correspond to relatively few microscopic configurations. So the cell has low entropy compared to a randomly mixed collection of the same molecules. Yet the second law still holds. How can a cell stay ordered in a universe that tends toward disorder? The answer is that the cell is not a closed system. It exchanges energy and matter with its environment. It takes in nutrients of higher free energy, expels waste and heat. In doing so, it reduces its own entropy, or at least maintains a low entropy state, while increasing the entropy of the surroundings. Overall, total entropy rises, but locally, order increases because the cell uses flows of energy to extract information from the environment, to build and maintain internal structure, and to replicate. This dynamic is present at many scales. Organisms, ecosystems, even technological civilizations maintain islands of order within broader, entropy-increasing processes. By channeling energy and processing information, you can think of a living organism as an information processing system that has been shaped by natural selection to detect regularities in the environment, to encode them in its structure, and to use them to act effectively. Sensors, from simple chemical receptors to complex eyes, collect data. Nervous systems or biochemical networks transform that data into internal states that guide behavior. If the organism can detect reliable patterns, it can respond in ways that increase survival, avoiding danger, finding food, seeking mates. In this way, information processing becomes a core strategy for controlling entropy locally. The organism does not violate physical laws. It pays for its internal order by exporting entropy, yet within its boundaries, it sustains improbable structures and maintains memories of past environments. In molecular sequences, in neural circuits, in learned behaviors, order can also emerge in systems that are not living. Whenever energy flows through matter under constraints, patterns may form. Chemical reaction diffusion systems can generate stripes, spots, waves, convection patterns. In fluids can create regular rolls or cells. Colliding galaxies produce spirals, shock fronts, and bridges of stars. These patterns are not imposed from outside. They arise from physical laws acting on systems far from equilibrium. Such systems can exhibit self-organization. They channel energy into particular modes that maintain structure, even as entropy increases overall. From an informational perspective, these structures represent constraints on how particles can be arranged. They carve out particular regions in the space of possible configurations, creating regularities that can in principle be detected and described. The connection between time, entropy, and information goes even further. In some modern approaches to fundamental physics, the very geometry of space-time may be related to informational quantities. The area of certain surfaces can be interpreted as a measure of entanglement entropy. The way regions of space are connected may reflect patterns of quantum correlation. Although these ideas belong to advanced research, they share the same spirit. Time and space are shaped not just by matter and energy, but by how information is distributed and how it changes. When we say that time flows forward, we are really noticing that information accumulated in records points one way. That entropy tends to increase, that processes which mix and spread information are vastly more probable than processes which concentrate it. The deep reason broken glasses are common and spontaneously unbroken glasses are effectively absent is not that physics forbids atoms from reassembling into a neat form. It is that the number of microscopic states that correspond to broken pieces everywhere is unimaginably larger than the number that correspond to intact glass. The reassembly would require an extraordinarily precise coordinated motion of countless particles, a state drawn from an almost measure zero subset of possibilities. Nothing in the laws of motion directly prevents it, but the informational structure of typical states makes it practically impossible. So we see only the one direction in which disorder grows and hidden information spreads. From this viewpoint, the universe can be pictured not only as a collection of particles and fields, but as a system that is constantly updating its informational configuration. At each moment, the actual state is one point in a vast space of possibilities. The laws of physics specify how that point moves, what transitions are allowed, which ones are extremely probable, and which ones are effectively inaccessible. The arrow of time is the path along which this state moves into regions with more available microstates, more missing information, higher entropy. Along the way, local subsystems can reverse the trend for a while by harvesting energy flows and reorganizing information within themselves. These are the temporary eddies of order within the larger current of increasing entropy. Living worlds, minds, cultures, technologies, all belong to this intricate dance between information and time. As you rest with this picture, you might imagine the universe itself as a vast computation, not in the sense of an artificial machine, but in the sense of a lawful unfolding of informational structure. Past states constrain what can happen next. Probabilities guide transitions. Records are laid down and rarely erased. Entropy increases as information about precise beginnings is diluted into countless degrees of freedom. Yet within that flow, new patterns arise. New correlations form, and local agents use information to navigate their surroundings. In this way, time, entropy, and information are woven together. The forward direction of time is the direction in which information about the past is preserved in records, and in which the detailed microscopic information about earlier states becomes harder and harder to reconstruct. The universe is not simply moving through time, it is continually rewriting its own informational content, moment by moment, in a way that, from our limited vantage point, looks like the steady forward flow of time. Imagine a star much more massive than our sun. It burns for millions of years, fusing lighter elements into heavier ones, holding itself up through the outward pressure of radiation against the inward pull of its own gravity. Eventually, its fuel is exhausted. The delicate balance between outward and inward forces fails, gravity wins, the star collapses. If the mass is great enough, nothing stops the collapse. Matter is crushed to extreme densities, and a new object is born. A black hole. A black hole is a region of space-time where gravity is so strong that once something falls in, there is no path that leads back out, not even for light. Around this region, there is a boundary, called the event horizon. If you cross this boundary, you cannot return, not because a wall is there, but because all possible paths lead deeper inward. Rather than outward, the event horizon is like a point of no return, for trajectories falling toward the center. From far away, a black hole can be described by a few simple numbers: its mass, its electric charge, its rate of rotation. These quantities determine the size and shape of the event horizon. A non-rotating, uncharged black hole has a perfectly spherical horizon. Its radius increases with mass. A rotating one is flattened, more complex in shape. Yet, despite the complicated, violent history by which the black hole formed, its external description is remarkably simple. This led to a saying that a black hole has no hair, meaning it has no visible details beyond those few parameters. Information about the specific matter that collapsed seems to be hidden behind the horizon. This raises a delicate question. What happens to all the information about the original material that formed the black hole? Imagine throwing an encyclopedia, a planet, a cloud of gas into a black hole. Each of those objects has a detailed internal structure, specific arrangements of particles, specific patterns. From an informational standpoint, they contain a huge number of bits. Once they cross the horizon, we no longer see them. From the outside, all we can measure is the increase in the black hole's mass, its spin, its charge, many different initial configurations, could lead to the same final black hole. So it appears that information about the original states is lost to outside observers. For a time, physicists thought that might be the end of the story. Information was simply trapped, perhaps forever, behind the horizon. Then in the 1970s, a new ingredient was introduced through the work of Stephen Hawking. He considered quantum fields in the curved spacetime around a black hole. Quantum theory tells us that even what we call empty space is not truly empty. It is filled with fluctuating fields in which pairs of excitations can briefly appear and disappear near a black hole's horizon. These fluctuations interact with gravity in a subtle way. Hawking's calculation showed that black holes should not be completely black. They should emit radiation with a temperature inversely related to their mass. This emission is very weak for stellar mass black holes and even weaker for larger ones, but in principle it is real. As the black hole radiates, it loses energy and therefore mass. If nothing falls in to replenish it, the black hole will slowly shrink over immense timescales. Eventually, it could evaporate entirely, disappearing in a final burst of radiation. This is where the information question becomes sharper. Suppose we begin with a complicated object, many particles arranged in intricate patterns. We throw it into the black hole. Its information appears to be hidden within the horizon. Then, over a very long time, the black hole evaporates through Hawking radiation. The final outcome seems to be just a cloud of radiation, smooth, thermal, characterized by a temperature and a broad distribution of energies. Thermal radiation is highly disordered. It corresponds to a state with very high entropy. Many different microscopic histories could have produced the same outward appearance. The detailed information about the infalling matter seems to have vanished, not merely hidden, but destroyed. This is the heart of the black hole information paradox. Why is that a problem? Because in quantum theory, the evolution of isolated systems is supposed to be reversible. Information about the past may become scrambled, spread out, encoded in complicated ways, but it should not be fundamentally lost, given perfect knowledge of the current quantum state and the laws of motion. One should, in principle, be able to reconstruct the prior state if black holes truly destroyed information by turning many distinct initial states into the same simple final state, purely thermal radiation. Then the evolution would not be reversible. It would violate a core principle of quantum theory. This clash between quantum reversibility and black hole evaporation sparked decades of debate and research. A major clue came from studying the entropy of black holes. Entropy, as we have seen, is a measure of how many microstates correspond to a given macrostate. In the 1970s, Jacob Bekenstein argued that black holes should possess entropy proportional to the area of their event horizons, not the volume. Later, using quantum field theory, Hawking's calculations confirmed this idea. He found a precise relation between the entropy, the surface area, the fundamental constants of gravity, quantum theory, and thermodynamics. The exact formula is technical, but the key point is simple. The larger the area of the horizon, the larger the entropy. So a black hole with a huge horizon can correspond to an enormous number of possible internal microstates from our informational viewpoint. This means a black hole has a vast capacity to store information, even though externally it appears to be described by just a few parameters. The complexity is hidden behind the horizon. The area acts as a measure of the information capacity. This area law is deeply surprising. In ordinary systems, entropy typically scales with volume. For example, the number of ways to arrange molecules in a box grows rapidly with the size of the box. The entropy is proportional to how much space is available inside. For black holes, the scaling is different. The entropy is proportional to the surface area. It is as if the true degrees of freedom reside on the horizon, not in the volume. This observation led to a bold conjecture. Perhaps in any region of space-time, the maximum amount of information that can be stored is proportional, not to volume, but to the area of its boundary. Perhaps the world at a fundamental level is encoded on surfaces rather than in interiors. This idea is known as a holographic principle. To understand the analogy, consider an ordinary hologram made with light. You start with a three-dimensional object. You record an interference pattern on a two-dimensional plate under suitable illumination. That plate can reconstruct the three-dimensional image, the information about the full volume is encoded on a surface in a highly non-trivial way. The holographic principle suggests something similar for space-time. Perhaps the physics of a region can be described by a theory defined on its boundary with one fewer dimension. The degrees of freedom inside the region would then emerge from the boundary description like a three-dimensional image emerging from a two-dimensional hologram. This is an abstract mathematical statement, not a literal claim that the universe is a projector screen. It says that there may exist equivalent descriptions of the same physics, one in terms of volume, one in terms of area, and that the area-based description counts information in units proportional to surface, rather than bulk in certain special kinds of curved spacetimes. This holographic idea has been made precise. Theories of gravity in a higher dimensional space have been shown to be mathematically equivalent to non-gravitational theories living on a lower dimensional boundary. These correspondences are highly technical, but their existence supports the broader thought that information in gravitational systems is organized in a holographic way, and that black holes are key examples of this organization. Returning to the information paradox, the holographic perspective offers a hint. If the full description of a region with a black hole can be encoded on its boundary in a way that follows the usual rules of quantum theory, then information might never be lost, even if, from a naive viewpoint, it seems to fall behind the horizon. The boundary theory keeps track of everything. The evaporation process becomes a unitary evolution in the boundary description where information is scrambled but preserved. This does not yet settle every detail. There are many proposals for how the information is carried away by the outgoing radiation. They involve subtle correlations that are extremely difficult to see in simple calculations, but the general consensus among many researchers now is that information is not destroyed. Rather, it is stored and later released in a highly scrambled form, consistent with the laws of quantum mechanics. Black holes, in this view, are not information erasers. They are information processors and containers, operating at the extreme edge of what nature allows. From a calm distance, we can summarize: black holes are objects where gravity and quantum theory collide. They challenge our notions of locality, of entropy, of information. They force us to rethink what it means for information to be hidden, preserved, or lost. They suggest that the fundamental bookkeeping of the universe may be governed not only by matter and energy, but by area, by horizons, by holographic relations between bulk and boundary. In that sense, black holes whisper that reality might be deeply informational, that what we see as mass and curvature may be the visible, gravitational face of a more abstract pattern of data encoded perhaps on surfaces interwoven with quantum states and evolving according to laws that ultimately respect the conservation of information, even in the darkest and most extreme places we know. Imagine holding a thin, flat, transparent plate. At first glance, it looks unremarkable. A small square of plastic or glass. Under ordinary light, you might only see a faint pattern of lines and speckles. But when you shine a suitable beam of light through this plate, something surprising appears in the space beyond. You see a three-dimensional image, a shape that seems to hang in midair, changing its appearance as you move your head, as if a real object were sitting there, even though there is nothing but the flat plate and the light. This is a simple example of a hologram. In a hologram, information about a three-dimensional object is encoded on a two-dimensional surface. The surface does not store a picture from one angle, like an ordinary photograph. Instead, it stores an interference pattern, a complex arrangement of bright and dark fringes created when light from the object interacts with a reference beam. That pattern looks unintuitive. It does not resemble the object itself, but it contains all the information needed for the light to later reconstruct the appearance of the object when illuminated correctly from different viewing angles. The brain receives different cues about depth and perspective, so the three-dimensional image emerges in experience from a flat source. A striking feature of many holograms is that each region of the plate contains information about the whole image. If you break the plate into pieces and illuminate one piece, you still see the entire object, but with less resolution, less detail. The information about the volume is distributed across the surface in a highly redundant and non-local way. This is important because it shows that a lower dimensional system can encode the appearance of a higher dimensional one, not by simple projection, but by storing patterns of interference that carry information about how waves combine and correlate. Physicists noticed that this idea has an intriguing echo in the behavior of black holes and in more general properties of space-time. We saw that the entropy of a black hole, the measure of how many microstates are compatible with its macroscopic appearance, is proportional to the area of its event horizon, not its volume. This area law suggests that, in some sense, the amount of information needed to describe everything inside the black hole scales with the boundary, not the interior. Gerard Hooft and Leonard Susskind were among the first to propose that this might not be a special property only of black holes. They suggested a more general principle that any region of spacetime may have a maximum information content proportional to the area of its boundary, measured in very tiny units set by the fundamental constants of gravity and quantum theory. In other words, the world might behave as if it were holographic, a higher dimensional volume described by data encoded on a lower dimensional surface. This proposal is known as the holographic principle. It is not a claim that our everyday world is literally a laser hologram projected onto a screen. Rather, it is a conjecture about how nature counts degrees of freedom, how it arranges its fundamental states. When gravity and quantum mechanics are both important, the principle says that the most complete, non-redundant description of everything happening in some region could be given by a theory living on the boundary with one fewer spatial dimension. The bulk physics inside would then emerge. From the boundary description, much as a three-dimensional image emerges from a two-dimensional hologram. For a long time, this idea was suggestive but not precise. That changed when theoretical physicists discovered concrete examples of such holographic dualities. One important example involves a particular kind of spacetime, sometimes called anti-de Sitter space. This is a universe with constant negative curvature. Its geometry is somewhat like a saddle, curved in one direction and in the opposite direction. In this special setting, it was shown that a theory of gravity in the bulk of this space can be mathematically equivalent to a quantum field theory defined on its boundary. The boundary has one fewer spatial dimension and no gravity. The bulk theory and the boundary theory look very different. They use different variables, different languages, and yet they produce exactly the same physical observables. Every state in the bulk corresponds to a state on the boundary. Every process in the interior has a dual description. As a process in the lower dimensional theory, in this correspondence, the bulk gravitational world can be viewed as a kind of hologram of the boundary and the boundary as a complete encoding of the bulk. This duality is highly technical. It requires specific conditions and symmetries. It is not our everyday universe. Yet it demonstrates that holographic behavior is not just a metaphor. It can be realized in precise equations. Many researchers believe that similar principles may apply more broadly, even if the details differ from the specific example observed so far. The core lesson is that what we normally think of as space-time geometry and gravitational fields can arise from an underlying structure of quantum information defined on a boundary, relationships, entanglement patterns, and correlation functions in the boundary theory mapped to distances, curvatures, and gravitational phenomena. In the bulk, geometry becomes a way of organizing information. This perspective has deep philosophical implications. It suggests that what we call space may not be fundamental. It may emerge from more basic ingredients, such as patterns of quantum entanglement between degrees of freedom. At the boundary, two regions of the boundary that are strongly entangled can correspond to 2 points in the bulk that are close together in geometric distance. If entanglement is reduced, those points move farther apart, or the bulk space can even tear. In extreme cases, in this way, the shape of space, its connectivity, its curvature, might be reflections of how information is shared and correlated at a more primitive level. Reality, in this view, is built, not from little solid bits, but from relationships, from structure, from the way systems are linked by quantum information. This can be unsettling, at first because it seems to contrast with our intuition of a solid world. filled with tangible objects. But the holographic viewpoint does not say that the world is fake or that experience is an illusion. Instead, it says that what feels solid and extended may be the macroscopic appearance of a deeper, more abstract order. The chair you sit on, the room you inhabit, the planet in its orbit are still completely real. They obey the familiar laws of mechanics, thermodynamics, and relativity. They can be measured, touched, lived in. What changes is our picture of what lies beneath. Those familiar laws at the deepest level. The universe may be better described as an intricate web of information and its transformations, with geometry and material fields emerging from that web. Rather than the other way around, structure becomes more fundamental than substance, relations more basic than isolated things. A gentle way to picture this is to think of a complex story told in many forms. You might hear it spoken aloud, you might read it in a book, you might watch it as a film. The physical media are different, but the pattern of events, the relationships between characters, the causal structure of the plot remain the same. The story is not the ink, not the sound, not the sequence of images. It is the abstract organization of these elements in a way that makes sense. The holographic idea invites us to see the universe as a kind of story, written in the language of quantum fields and gravity, or in the language of boundary theories with entanglement and correlations. Each description uses different symbols, different medium, but they encode the same underlying structure. That structure is informational. It is about which states are allowed, how they connect, how they evolve. Another analogy is a mathematical object, such as a symmetry group. You can realize it in many physical systems, rotations of a sphere, permutations of labels, actions of matrices. The realizations differ, but the abstract group is the same. Its elements, its relations, can be studied independently of any particular realization. Similarly, the relational structure of the universe may be independent of the particular picture we use, whether we imagine a four-dimensional space-time filled with fields or a lower-dimensional boundary with interacting quantum degrees of freedom. The holographic principle says these descriptions can be dual, two views of one underlying informational reality. Through this lens, the question, is reality made of information, takes a more precise form. We are not saying that the world is literally composed of bits like the storage in a computer chip. We are saying that the most fundamental description may involve states and relations that behave like information, quantities that can be counted, transformed, entangled, compressed, and encoded on surfaces in ways that determine what happens in volumes. Physical laws become rules for how information is allowed to flow. Conservation laws become statements about constraints on that flow. Geometric properties become emergent summaries of how deeply entangled different parts of the system are. Crucially, this does not drain the universe of meaning. It does not diminish the richness of experience. Instead, it suggests that meaning and pattern are woven into the foundation of things, that the ability to form stable structures, to sustain order, to create complexity, is rooted in the deep informational fabric of reality. The holographic perspective shows how even space itself might arise from that fabric. Not as an illusion, but as a large-scale manifestation of more ancient and subtle relations hidden beneath our everyday view. As you breathe gently, you might imagine the cosmos not as a huge box filled with separate objects, but as a vast, interconnected hologram, where every region carries information about many others, where boundaries hold clues to interiors, where the three-dimensional world you move through is one realization of an underlying pattern. That might also be written on some distant, abstract boundary in fine, mathematical detail. Whether or not this picture is exactly correct, it offers a calm and striking lesson. That reality may be less about stuff and more about structure, less about isolated pieces and more about the relations between them. In that sense, the universe begins to look like an immense lattice of information in which everything that is defined by how it fits into the whole. Imagine stepping back far enough that the entire universe looks less like a collection of objects and more like a process, a vast unfolding of states linked together by quiet, persistent rules. At each moment, the cosmos has some configuration of fields, particles, curvatures of space-time. In the next moment, that configuration is updated according to laws. We call those laws the laws of physics. from this vantage point, the universe begins to resemble a computation, not in the sense of numbers in a calculator, but in the sense of a system that repeatedly transforms input states into output states, following stable rules over and over on every scale. One of the physicists who expressed this idea with unusual clarity was John Archibald Wheeler. He proposed a phrase that has become famous, "it from bit." He meant that every physical thing, every particle, every field, every chunk of space-time might ultimately derive its meaning, its existence from bits, from answers to yes or no questions, from elementary units of information. In his view, the world is not built from solid bricks, but from acts of distinction, from the outcomes of fundamental questions. Is the field here or not? Is the particle in this state or that one? Each such distinction is a bit, and from piles of bits, more complex structures are built. This is a radical perspective. Yet it connects with ideas that computer science and mathematics have been exploring for decades. Consider a cellular automaton, a simple computational model. Imagine a grid of cells. Each cell can be in one of a few states, for example, black or white, on or off. At each step, the state of each cell is updated according to a rule. The rule depends on the current state of that cell and of its neighbors. All cells update in parallel. Time advances in discrete ticks. Tick by tick, the pattern evolves. What is remarkable is that even very simple rules can produce surprisingly rich behavior. Some rules lead to static patterns that quickly freeze. Others produce periodic structures that repeat. Still others generate patterns that never exactly repeat, that show localized structures, moving, colliding, combining. Sometimes these systems can support logical operations, storage of information, even self-replicating patterns, all from extremely simple underlying rules. Some cellular automata are known to be universal, meaning they can emulate any computation that any digital computer can perform. Given enough time and enough space, they can simulate other cellular automata, physical systems, mathematical algorithms, even themselves. In this sense, they show how a world built from simple bits, updated by simple rules, can nevertheless display complexity, emergence, and long-range structure without any extra machinery. Hidden inside, when Wheeler spoke of it from bit, and when others developed the idea of digital physics, they were not claiming that the universe literally is one of these specific automata. Instead, they were asking whether the success of computational metaphors might hint at something deeper. Could it be that the laws of physics are themselves algorithms that update informational states, step by step? Could the familiar continuum of space-time be an approximation to a discrete structure with an underlying mesh of bits that flip according to fundamental rules? We do not yet fully know. Modern physics describes space-time as a smooth manifold, a continuous fabric on which events are located at specific coordinates. Quantum field theory describes fields as continuous entities defined at every point in space and time. These descriptions are extremely successful. They predict experiments with extraordinary accuracy, yet they may not be the last word. There is a natural question: is space-time truly continuous, or does it have a smallest scale, a fundamental graininess that we cannot yet resolve? There is a characteristic scale built from the constants of nature, gravity's strength, the speed of light, and the quantum of action combined. They define a length so tiny that it is far beyond any direct experimental reach. This length is often spoken of as a candidate for the smallest meaningful distance. If space-time has a discrete structure, it might be woven from cells on the order of this length. Of course, we do not yet know if this is really so, but many approaches to quantum gravity hint at discreteness. Spin networks, causal sets, and other models represent space-time as a web of elementary units linked by relations rather than as a smooth continuum. If this picture is right, then the universe would have something like pixels, but in 4 dimensions, not 2. Events would be nodes in a vast causal graph where each link represents a fundamental relation of before and after. The laws of physics would be rules for how such graphs can grow, which patterns are allowed, which transitions have non-zero probability. The familiar continuum of space and time would emerge at large scales from the statistics of many underlying relations, much as a smooth fluid emerges from the motion of countless molecules and a continuous image emerges from the fine grid of pixels on a screen. In this kind of view, particles are no longer tiny billiard balls flying through space. Instead, they become features of the underlying information. They are excitations, patterns, stable structures in a deeper substrate. They might correspond to certain configurations of bits or of more abstract units, of information that repeat and propagate, maintaining identity over time. A particle's mass, its charge, its spin would then be properties of the pattern, not of a solid core. The particle would be a localized bundle of information, interacting with other bundles according to rules that look like forces and fields at the emergent level. To make this concrete, you can think again of cellular automata. In some automata, certain shapes move across the grid without dissolving. These shapes are not separate objects, they are recurring patterns. In the states of the cells, if you change the rule, you change which patterns are stable, which can propagate, which can interact. The rule is like the law of physics. The patterns are like particles. If you watch only the patterns, you would infer effective laws about how they move, collide, and combine. You might never see the underlying grid if your observations are coarse relative to it. Digital physics asks whether our universe is analogous to such a system, but vastly richer with rules chosen by nature rather than by us. Some theories use ideas from computation to frame questions about the universe. Is there a limit to how much information can be stored in a given region? We have seen hints that the maximum may scale with surface area. Is there a limit to how quickly information can be processed within physical systems? If so, there might be. Ultimate bounds on computation, energy, and time are linked. Constraints on energy translate into constraints on elementary operations over a given interval. These ideas connect deep physics to the performance of any possible computer. However advanced, it might be even a hypothetical machine built by a civilization far beyond ours would still obey the same physical limits set by the structure of reality. If reality is informational, then computation is not just something we do with devices, it is something the universe itself is constantly engaged in. In recent years, another idea has captured public imagination, the possibility that our observable world might itself be a kind of simulation, a virtual environment, generated by some deeper layer of reality. This simulation hypothesis is a philosophical speculation, not an established theory. It raises questions about whether observable properties, such as discreteness or specific limitations, could reveal an underlying computational substrate. Scientists who consider such possibilities typically treat them with caution. They ask what empirical signatures would distinguish a fundamental digital universe from one described by continuous mathematics. Are there tests we could perform to decide, or are many versions of the idea not testable at all, in which case they belong more to metaphysics than to physics? Leaving aside strong claims about simulations, it remains scientifically fruitful to treat the universe as if it were an information processing system. This framing has already led to insights in quantum information theory, black hole thermodynamics, and the holographic principle. It encourages questions like how many bits are needed to describe a black hole of a given mass, how much entanglement is required to knit together a smooth space-time, how does the pattern of quantum correlations change as the universe expands or as matter collapses into dense objects. These questions do not require us to imagine programmers or external simulators. They simply use the language of information as a tool for expressing physical law at a deep level. From a calm, conceptual standpoint, you can picture the universe as following update rules at every location and every moment. In ordinary differential equations, this updating is described continuously. The rate of change of each quantity depends on its current value and perhaps on others. The updating occurs in steps. In either case, the essence is similar. The state now determines the state. A moment later, within the constraints of the laws, the universe does not look ahead to some final goal. It simply follows its own rules, transforming information about the present into information about the near future over and over. This way of seeing has a certain quiet beauty. It suggests that every event, every interaction, every quantum jump is part of a great ongoing computation carried out by the universe on itself. Matter, energy, space-time are both the hardware and the data. There is no separate machine outside running the program. The machine and the program are one and the same, viewed at one level. We speak of particles, fields, and forces. Viewed at another, we speak of bits, states, and update rules. Both languages describe the same reality from different angles. In this light, the question, is reality made of information, does not require us to imagine that the universe is only a digital code. Instead, it invites us to notice that everything we can describe about the physical world can be cast as statements about states, possibilities, and the rules that connect them, that the constraints we call laws can be thought of as computational rules, that the limits we encounter on energy, speed, and precision can be expressed as limits on information processing. If this perspective continues to prove fruitful, then it may be that at the deepest level, the language in which reality is written is not the language of solid objects, but the language of information, and that the universe, in its calm, unhurried unfolding, is a vast, subtle computation, writing and rewriting the code of its own existence. Your brain is a piece of matter, but it is also a flowing pattern of information. Billions of cells, each with branching trees of connections, signals rising and falling, in quiet rhythms, always changing, yet somehow maintaining a sense of you through time. One way to see the brain is as an organ whose primary task is to process information, not information, in the everyday sense of news headlines or written words, but information in the deeper sense of patterns in the world that make a difference. For survival, differences between light and dark, between food and poison, between friend and threat, between safe path and dangerous cliff. The nervous system takes in signals through receptors, transforms them, combines them, compresses them, and turns them into actions, into changes, in muscles, in hormones, in further brain activity. Your experiences are entangled with this continuous cycle of sensing, predicting, acting, and learning. At the microscopic level, neurons communicate through electrical impulses and chemical signals. A neuron sits in a bath of ions, charged particles, pumps and channels in its membrane, maintain differences between inside and outside. When certain inputs arrive, these differences can suddenly shift, producing a brief pulse of electrical activity that travels along the neuron's length. When the pulse reaches the end, it triggers the release of molecules into the gap between cells. These molecules bind to receptors on the next cell, changing its state, making it more or less likely to fire its own pulse. This chain of cause and effect extends through intricate networks of neurons across multiple regions of the brain. From an informational standpoint, each neuron is like a small element that encodes a variable. Its pattern of firing over time conveys something, not in words, but in timing, in frequency, in combinations. The brain uses many different codes. In some systems, the rate of firing over a short interval carries information. In others, the precise timing of spikes matters. Groups of neurons can form assemblies whose coordinated activity represents a stimulus, a memory, a plan, or a learned association. If you look at the visual system, for example, you see layers upon layers of processing. Cells in the retina respond to simple features like spots of light. Cells in deeper areas respond to edges, orientations, motion. Later stages respond to complex shapes, faces, objects, scenes. At each stage, the incoming information is transformed into a new code that emphasizes what is useful and discards what is redundant or irrelevant. This is compression, abstraction, inference carried out by living tissue. A common theme in modern neuroscience is that the brain is not just a passive receiver of information, it is an active predictor at any moment. Your brain is constantly generating expectations about what will happen next, about what you will see, hear, feel. It uses prior experience to form internal models of the world. When new sensory data arrives, it is compared to these expectations. If the data matches the prediction, very little needs to change. If there is a mismatch, an error signal arises. This error propagates through the system, updating the internal model or adjusting behavior to reduce the discrepancy. In this view, perception is not simply reading inputs. It is a process of minimizing surprise, of reducing prediction error across many levels of the brain, moment by moment. This perspective is sometimes called predictive processing or predictive coding. It treats the brain as a hierarchy of models. Higher levels capture more abstract patterns such as objects, contexts, and causes. Lower levels capture more immediate details, such as edges, textures, sounds. Signals flow downward, carrying predictions, and upward, carrying errors. The overall dynamic is one of constant adjustment. The brain seeks internal states in which its predictions fit its inputs as well as possible within the constraints of its limited resources. In this way, it performs a continuous information-theoretic optimization, balancing complexity, accuracy, and efficiency. From another angle, you can think of each conscious moment as the brain's best guess about the hidden causes of its sensory inputs. When you see a cup on a table, you are not directly experiencing patches of light and shadow. You are experiencing the brain's inferred cause of those patterns, an object with a certain shape, material, and location. Your sense of a stable world is the felt side of this inferential process. Your experiences are the content of your brain's model of what is out there and of what you are within it. If reality is fundamentally informational, then this relation between brain and world takes on a special character. There is information out there in the environment, in the arrangement of photons, in the vibrations of air, in the chemical gradients around you. There is information in here, within the brain, in patterns of firing, in synaptic strengths, in the structure of neural networks. Conscious experience arises at the interface between these two domains. The brain, as an information processing organ, constructs a structured model from structured inputs. You, as the subject, are what it feels like from the inside when one particular model is running on that organ. In that body, in that world, some theories try to go even deeper. They ask whether consciousness itself can be characterized in informational terms. One such attempt is called integrated information theory. The basic idea can be sketched in gentle strokes. The theory proposes that for a system to support consciousness, it must generate information as a whole that is more than the sum of its parts. If you cut the system into pieces, each piece should lose some of the informational structure that was present only when the system was intact. In more technical language, the system's causal structure must be integrated. That is, its current state must make a difference to its own past and future in ways that cannot be localized purely to independent fragments. The quantity of such integrated information is sometimes denoted by a symbol and is proposed as a measure of how much consciousness the system has. The specific mathematics is subtle, and ongoing research continues to refine it, but the conceptual message is that consciousness might be related to how information is organized and interlinked within a physical system, not simply to how many bits it carries, but to how deeply those bits depend on one another. In a different line of thought, another framework, called the free energy principle, suggests that living systems maintain their order by minimizing a quantity related to surprise or uncertainty about their sensory inputs. This free energy is not just a thermodynamic concept used in chemistry. It is a broader information-theoretic measure that bounds how surprising incoming data can be given the system's internal model. Under this principle, organisms are seen as entities that keep themselves within a limited range of states by acting, perceiving, and learning in ways that reduce expected surprise. They update their internal models to better predict inputs, and they move in the world to seek situations that match their predictions. This continuous loop of perception and action is again a process of information management. The system tries to remain in a narrow region of its vast space of possible states by controlling the flow of information across its boundaries. In this view, a mind is something like an information engine that spends energy to reduce uncertainty about its environment and maintain its own structure over time. If you step back from the technical details, a common picture emerges. The brain is not just a lump of tissue reacting blindly to stimuli. It is an intricate system that continually constructs models, compresses inputs, predicts consequences, updates beliefs, and guides actions, all in the service of preserving the organism in a changing world. Consciousness is entangled with this process. Your experience is filled with structured content, objects, spaces, times, relations, emotions, thoughts. All of these are informational structures within the brain's model of world and self. If reality itself is made of information at the deepest level, then a conscious system is a special pattern of information within that broader fabric. It is a pattern that encodes not only the outer world, but also its own existence. It models itself as an agent, distinguishing between me and not me, between internal states and external causes, between actions and outcomes. This self-model is not an illusion in the sense of being unreal. It is a functional construct that allows the system to coordinate its own behavior, to plan, to remember, to imagine, and to choose within constraints. The question, what is a perceiver, becomes what kind of informational structure can play the role of a subject of experience. One answer, from the perspectives above, is a system that maintains a coherent, integrated model of the world and of itself, that uses this model to minimize surprise and to guide action, that has states which are richly informative about both the external and internal conditions, a system whose informational architecture is not just a collection of independent parts, but a deeply intertwined network, where changing one part has consequences for many others. From this calm vantage point, there is no need to invoke anything mystical. Consciousness does not have to be a substance added on top of matter. It can be seen as a way certain kinds of informational processes feel from the inside when they reach a sufficient level of complexity and integration. Brains are one example, perhaps not the only one, but the most familiar to us. At the same time, we do not fully understand why specific patterns of neural activity give rise to the specific qualities of experience, why this arrangement of information feels like red, and that arrangement feels like pain or warmth, or the sense of being a self. There is still a large gap between our current theories and a complete explanation of subjective life. This gap is sometimes called the hard problem of consciousness. Even within an informational framework, we can say much about structure, about processing, about functions, but the direct link to felt experience remains partly hidden, at least for now. Yet, even with this humility, the informational lens offers a gentle, coherent way to hold the mystery. If reality is patterned at every scale, if information is written into atoms, into space-time, into black holes, into quantum fields, then it is perhaps less surprising that information also organizes itself into systems that can know that they exist in such a universe. Your awareness is a local region, where the cosmos has become aware of some of its own structure through a biological instrument, shaped by evolution and continuously updated by experience. You are not separate from the informational fabric. You are one of its most intricate folds, temporarily stabilized by the body and brain that host you. As you let these thoughts drift and soften, you might imagine conscious minds as eddies in a vast informational river. Each eddy has its own whirling pattern, its own inner view. The river is the universe itself, flowing, computing, rearranging information, moment by moment. Even when any given eddy dissolves, the river continues, the underlying fabric remains. In that sense, a perceiver is a transient, yet real, configuration in which information has folded back on itself to form a model that includes the one who is modeling. It is a quiet, remarkable thing to be such a configuration for a while in a universe that may itself be written in the language of information. Close your eyes for a moment and picture something simple: a tiled floor, a row of trees, a night sky filled with evenly spaced stars. Your mind tends to relax when lines are straight, when spacing is regular, when patterns are clear. Now picture a floor where tiles have random sizes, random angles, where tree trunks twist in erratic directions, where stars are scattered in clumps and gaps with no visible rhythm. You might feel a slight tension, a sense that something is off, without quite knowing why. Humans are deeply sensitive to pattern. Your visual system is wired to detect edges, symmetries, repetitions, regularities. Your auditory system finds rhythm in sound, beats, melodies, harmonies. Your cognitive system looks for cause and effect. If this happens, then that happens. Stories, explanations, rules, all of these are ways of compressing information, of taking something complex and summarizing it in simpler terms. Pattern is a form of informational economy. When you find a pattern, you need less memory to store what you see. Every second tree in this row is shorter than listing the height of each tree individually. Every day the sun rises in the east is a single rule. Instead of a million separate memories, your brain loves these compressions because they save energy, reduce uncertainty, and help predict what comes next. That is one reason patterns comfort us. They make the world more predictable. When you walk into a room and objects are where you expect them, you relax. When your close relationships follow relatively stable rhythms, you feel safe. When the seasons arrive in familiar order, it is easier to plan, to adapt, to live. Your nervous system has evolved in environments where noticing patterns meant the difference. Between life and death, knowing which clouds mean storm, which tracks mean predator, which sounds mean friend or foe, pattern recognition was survival long before it became aesthetic pleasure. Randomness is different. Pure randomness is patternless. Every outcome is independent of the previous one in a perfectly random sequence. There is no shorter description than the sequence itself. No compression, no underlying rule. For your brain, this is both difficult and unsettling. When events seem random, it is hard to know what to expect, to form reliable models, to prepare your predictive machinery. Struggles, prediction errors increase, and with them a sense of uncertainty or unease. This is why random losses, random noise, random failures often feel worse than structured ones. Even if on paper the statistical risks are the same, an unpredictable world demands more. From your nervous system, it must constantly adapt, revise expectations, search for patterns, even when none are there. This can be exhausting. Of course, the universe is not purely ordered or purely random. It is a mixture of lawful regularities and stochastic fluctuations between the extremes. Your mind tries to find the right balance. Too much rigidity, too much order can feel stagnant or oppressive. Too much chaos, too much noise can feel terrifying or meaningless. A rich life often lies somewhere in between, where there is enough pattern to feel stable, but enough novelty to feel alive. Culture grows in this space between order and randomness. Culture is shared information held across many minds and many artifacts. Languages, customs, beliefs, technologies are records of patterns discovered and preserved over generations. A language is a vast system. For compressing and sharing information, words are labels. For recurring structures in experience, grammar is a pattern for combining those labels into more complex meanings. When you learn a language, you are internalizing a shared code, a way of representing the world and your own mind in informational form. Once you share that code, you can exchange inner states with others by breathing out sequences of sounds or writing down sequences of symbols. Culture is the accumulation of such shared codes. Songs, myths, scientific theories, legal systems, norms, all are patterns that live not in one brain but in many. Notice how stories occupy a central place in culture. A story is a structured sequence of events linked by causality, motivation, or symbolism. It helps make sense of scattered experiences by placing them in a coherent order. When you tell the story of your day, you select a few key moments, arrange them, and connect them into a narrative. This is a way of compressing and organizing information about what happened so that it can be remembered, shared, and understood. Your entire identity, in many ways, is a story. You tell yourself about who you are, where you came from, what you value, where you are going. This story is not arbitrary. It is constrained by many things, by your actual history, by your body, by your relationships, by your society, but it is still an informational construct, a pattern. In the brain's activity, a recurring way of interpreting your own experiences, when you say, "I am this kind of person," you are summarizing many episodes into a compact formula. Your sense of self is a living narrative, continuously updated by new input and new reflection. Memory is another way. Your life becomes an informational structure. The events you live through do not remain in the physical world. They pass, they end, yet traces of them persist in your nervous system. In the strengths of synapses, in the patterns of connectivity, in the dispositions of circuits. To activate together, a memory is not a perfect recording. It is a pattern that can be reconstructed later, when cues are present or when you deliberately recall it. Each time you remember, you rebuild the experience from stored information and from your current context. Over time, memories change, details blur, emotional tones shift. Some episodes are reinforced, replayed, and strengthened. Others fade into the background. From an informational viewpoint, your remembered life is like a compressed archive of the actual stream of moments lived. You cannot store everything, so your brain chooses what to keep, guided by salience, emotion, utility, and repetition. What remains is your personal universe history, a subset of everything that happened. encoded as patterns within you. Love can also be seen through this lens. It is not reduced to information that would strip away its warmth. Instead, we can say that love is a pattern of value and connection that organizes information about another person in a special way. When you love someone, their states matter enormously to your own. Their joy, their pain, their presence or absence all carry high informational weight. Signals about them have priority in your attention. Their well-being is entangled with your own. You build a rich internal model of who they are, how they feel, how they might respond. You anticipate their needs, remember their preferences, integrate their story with yours. Your nervous system allocates a great deal of capacity to representing this shared structure in the combined lives. Love is therefore a high-bandwidth connection between informational states. It changes how you process the world, how you plan, how you evaluate what matters. It is not just a feeling. In isolation, it is a reconfiguration of your internal models and your priorities, so that self and other are no longer completely separate. Even social identities are informational patterns to say, I belong to this group, or I follow this tradition, is to align your internal models with a larger shared structure. You adopt certain narratives, symbols, and rules. You store them in your mind. You act them out. In behavior, you transmit them to others through teaching, imitation, or influence. Groups are networks of information exchange. Norms, expectations, reputations are all ways of stabilizing patterns across many individuals. It is not that these things are unreal. On the contrary, they can be very powerful, but at their core, they are arrangements of information in brains and in external media, rather than separate substances. If we take all of this together, pattern recognition, culture, memory, identity, love, we begin to see the human experience as a rich informational landscape. Your life is not just a sequence of physical events, it is a continuous process of encoding, decoding, storing, and transforming information. You are both the medium and the message. Your brain and body provide the physical substrate. Your experiences are the flows and patterns that pass through that substrate and leave traces behind. So if reality at its deepest level is made of information, or at least can be described in informational terms, does that make it less real, less meaningful, less sacred? The answer is gently no. Information is not an abstraction floating outside the world. It is a way of talking about structure, about relations, about constraints. The patterns we see in physics, in chemistry, in biology are real. Their informational descriptions are simply ways of capturing those regularities in precise form. Saying that the universe is built from information is like saying it is built from relationships, from ways things depend on one another and fit together. Your experiences, your values, your connections are part of that fabric. They are not illusions painted on a meaningless background. They are specific, intricate patterns in the informational field of the cosmos. Think of a piece of music. On one level, it is vibrating air. On another, it is a sequence of tones, rhythms, and harmonies. On yet another, it is a structure that evokes emotion, memory, and imagery. You can describe it as physics, as notation, as feeling. None of these descriptions makes the others less valid. They simply highlight different aspects of the same phenomenon in the same way. Describing reality as information does not erase the richness of its content. It offers another level of understanding about how that richness is organized and sustained. When you look up at the night sky, you see pinpoints of light. Each star is a thermonuclear engine, burning hydrogen into heavier elements. But it is also a source of information. Photons carry data about its temperature, its composition, its motion, its history. When those photons reach your eyes, they change the state of your brain. You become a little more informed about a distant region of the universe. Your awareness expands by a tiny increment. This exchange is not metaphorical. It is a real flow of energy and information across vast distances. In that moment, your inner experience and the outer cosmos are linked by the same physics that governs everything, atoms to galaxies. From this perspective, meaning is not something added on top of a dead universe by isolated minds. It is a name for particular kinds of informational relations. When something is meaningful to you, it occupies a dense web of connections in your internal models. It ties together memories, values, predictions, and feelings. It has high impact on your decisions, on your future states. Meaning is the way. Some patterns resonate more deeply within your structure than others. A universe in which such resonance is possible is not empty, it is fertile for significance. So even if the foundation of reality is informational, even if space, time, matter, and mind are all aspects of one vast structured field, your day-to-day life remains what it always has been: moments of experience, moments of connection, moments of quiet and of change. The informational view does not tell you which relationships to cherish, which projects to pursue, which stories to live by, but it can offer a unique kind of comfort. It suggests that pattern and structure are woven deeply into the cosmos, that your own search for order, for understanding, for coherence is not alien to the universe. It is one mode in which the universe expresses its own pattern nature. As you rest, you can let this idea settle gently. Your thoughts are patterns, your memories are patterns, your relationships are patterns, your culture is woven from patterns. The galaxies above, the atoms within, are patterned too. At every scale, reality seems to favor structure over chaos, to allow islands of order amid expanding entropy, to support systems that can know and care and remember. If that is what it means for reality to be made of information, then you, as a conscious feeling being, are not outside that story. You are one of its most intricate chapters, written for a time in a language of patterns and relations and quietly unfolding information. When we speak of reality as information, of space-time as emergent, of the universe as computation, it can sound seductively complete, as if a single idea might finally explain everything. But in calm reflection, it is important to notice the edges of what we actually know, to see where evidence ends and speculation begins, to remember that even the most elegant picture is still a picture drawn by finite minds trying to understand an immense and quiet universe. Digital physics, in its broadest sense, is the suggestion that the world can be fundamentally described in informational terms, that bits, states, relations, and rules may be more basic than stuff. Yet this suggestion does not mean, and should not be taken to mean, that reality is a literal computer program running on some hidden machine. It does not mean that every detail of the universe is already correctly captured by our current models, or that we are close to a final theory. It does not mean that everything continuous is an illusion, or that space-time is definitely pixelated. It does not mean that meaning or consciousness have been fully explained in simple codes. At most, it says that information is a powerful language for expressing physical law, and that many deep puzzles seem to point in that direction. Consider what digital physics does not yet do. It does not give us a single unified framework as widely accepted as quantum field theory or general relativity. There is no standard information-first equation to write down, no universally agreed informational ontology. Instead, there are many proposals and perspectives. Some treat space-time as emergent from entanglement. Some focus on discrete networks of events. Some emphasize holographic dualities. Others think in terms of computation or codes. These projects share a family resemblance, but they are not yet one coherent theory with clear, testable predictions. Across all domains, they are more like bright constellations of ideas in a sky we are still mapping. There are also competing interpretations of quantum mechanics and of fundamental physics that do not assign any special status to information in an ontological sense. For example, some physicists treat the wave function as a real physical field, spreading over configuration space. The mathematics is the same, but the emphasis is on what there is, rather than on what can be known or encoded. In this view, information is derived from that field, not the other way around. Others adopt an instrumentalist stance. They regard the quantum formalism as a tool for predicting outcomes of experiments, not as a literal description of microscopic reality. In that approach, information is about measurement records and probabilities, but we are warned not to reify it into a substance from which reality is made. Even among those who take information seriously as a physical quantity, there is debate about what this means. Some say information is always information for someone or for some agent, that it is a relational concept, not an independent building block. Others argue that information can be defined objectively in terms of correlations between physical systems without any observer being present. These nuances matter because they shape what it means to say that reality is information. Is information a fundamental thing, like mass or charge, or is it a way of talking about constraints and relations in already existing stuff? Does it exist before any possible knower, or only in relation to systems that can store and process it? The answers are not settled. There is also an important distinction between digital and analog pictures of the world. Digital physics, in its strictest form, says that reality is discrete, that there is a smallest length, a smallest time step, a finite number of degrees of freedom in any region of space-time, but our best current theories are written in the language of calculus. They treat fields as continuous, space-time as smooth, differential equations as exact. Some researchers believe that underneath these continuous models there must be a discrete layer. Others suspect that continuity is truly fundamental, and that discrete models are approximations useful for computation or intuition, but not literally. How nature is built. For now, the evidence is ambiguous. We have not yet probed scales small enough to decisively reveal granularity or to rule it out. Methodologically, there are limits to what can be inferred from information-theoretic reasoning alone. Many arguments about black holes, entropy, and holography rely on thought experiments, on extrapolations of known formulas into regimes we cannot yet access. Experimentally, these arguments are powerful but not infallible. They assume that certain relationships continue to hold under extreme conditions we have never directly tested. Until experiments or observations reach those regimes, we must keep in mind that nature may surprise us. The measurement problem in quantum mechanics also remains only partially tamed. Describing quantum states as information can clarify certain puzzles. It can emphasize the role of correlations and the update of knowledge when measurements occur, but it does not fully dissolve all questions about how and when definite outcomes arise. Is collapse a real physical process? Is the universe forever branching into many worlds? Are measurement outcomes simply the experiences of observers whose own brain states become entangled with the systems they observe? Each of these views can be dressed in informational language, but the core issues are not yet universally agreed. Information helps us talk, but it does not automatically solve every conceptual knot. Ongoing debates in quantum gravity offer another example. Some researchers argue strongly for holographic descriptions and emergent spacetime. Others work on approaches that remain closer to the traditional continuum. Some focus on loops and discrete geometries, some on causal sets, some on tensor networks. Each approach has successes and challenges. The information-centric views often shine in explaining entropy bounds, black hole behavior, and aspects of quantum field theory in curved spacetimes, but they can be more abstract when it comes to reproducing the full richness of our cosmos with all its galaxies, structures, and precise numerical parameters. We are still far from deriving a unique universe from first principles written entirely in informational terms. There is also the subtle issue of empirical distinguishability. If two different fundamental pictures make exactly the same predictions for all possible experiments, then physics cannot tell us which is really true. Information-first models may be formally dual to more traditional field theories. In such cases, the choice becomes a matter of interpretation, of philosophical preference. Rather than observable difference, this does not make the information view wrong, but it does remind us that nature can often be described in multiple ways, equally valid from the standpoint of measurement. On the practical side, many of the most exciting ideas about information in fundamental physics have been developed in highly symmetric toy models, anti-de Sitter spacetimes, conformal field theories, simplified black holes, entanglement structures in idealized settings. The universe we inhabit appears to have a different large-scale geometry, with accelerated expansion, messy matter content, and many broken symmetries, extending holographic dualities and information-based constructions. To such a universe is an active project, but not yet complete. The story is still being written, and large parts remain blank. All of this points to a simple but important message: the idea that reality is information is not a finished doctrine. Handed down as truth, it is a research program, a lens, a guiding metaphor that has already yielded striking insights, but that must still pass many tests. It coexists with other lenses, field-based, geometrical, relational, each of them highlights different features of the same underlying world. When we forget this, when we treat any one picture as final, we risk turning science into dogma rather than an open-ended inquiry. Scientific humility is not skepticism. For its own sake, it is a recognition of scale. Our theories are compressed summaries of limited data constructed by minds of finite capacity within a small region of space and time. It is almost certain that they are incomplete, perhaps in ways we cannot yet imagine, yet within their domains they work and they guide us to new experiments, new technologies, new questions. Humility is the attitude that holds both truths at once. Our knowledge is powerful and partial. Our models are accurate and approximate. Our understanding is deep and unfinished. In the context of digital physics, humility means acknowledging that information is a very useful concept, but perhaps not the only or ultimate one. It means remembering that our current formulations are stepping stones, not endpoints, that tomorrow's theories may rewrite what we now consider fundamental or may show that information itself is emergent from something even more general that we have not yet named. It means being willing to update our deepest intuitions in light of new evidence, in the same way we update less personal beliefs about smaller things in a quiet way. This humility can be comforting. If you sometimes feel uneasy about not knowing exactly what the universe is or why it exists or what consciousness truly is, you are sharing the same uncertainty that the entire scientific community lives within. There are no final answers yet, only gradually improving maps. What matters is not reaching some final point beyond all questioning, but participating in the ongoing process of refining our understanding, step by step, observation by observation, thought by thought. Seen from this angle, science is itself an information process. The universe presents patterns in the form of data. We propose models, compress those patterns into laws, test those laws against new observations, keep the ones that work, discard or revise the ones that do not. Over time, our collective knowledge becomes a growing shared structure, stored in books, in instruments, in digital archives, and in trained minds. What we call physics is one part of the universe's information about itself, accumulated by creatures who evolved to notice patterns and ask questions. You are one of those creatures lying here, thinking about information in a universe that may itself be informational. There is a quiet symmetry in that. So when you hear that reality might be made of information, you can hold the idea gently without clinging. You can appreciate the elegance of holographic principles, the depth of entropy, the hints that space-time and gravity may be emergent from more abstract relations. You can be intrigued by the phrase, it from bit, and by the image of the universe as a computation, but you can also let these ideas sit alongside other possibilities, fields, waves, geometries, stories, and accept that our current view is a snapshot in an ongoing exploration, not a final verdict. In the end, the attitude that suits a universe like this may be quiet curiosity, a willingness to look, to listen, to model, to test, and to accept that mystery will likely remain. Even as understanding deepens, we can know more without knowing everything. We can be at peace inside an unfinished, yet ever more intelligible cosmos. We can rest in the thought that to exist here is to be part of a vast open question, one that reality is continually asking of itself. You are lying here inside a universe that has been unfolding for billions of years. Stars have formed, burned, and faded. Galaxies have collided and drifted apart. Clouds of gas have collapsed into suns and planets. On one of those planets, life has emerged. Cells have divided, organisms have adapted, brains have evolved, and somewhere along that long chain a mind appeared that could ask what all of this means. That mind is yours right now. You have followed a quiet thread through ideas about information, about matter, about time, about black holes and quantum states, about brains and experience and patterns. You have seen that the universe can be described in many languages: particles and forces, fields and geometry, energy and entropy, bits and codes. None of these languages are the universe itself. They are ways of understanding, ways of compressing what we observe into structures the mind can hold. There is a gentle relief in recognizing this. You do not have to decide tonight which language is the ultimate one. You do not have to solve the deepest equations or settle the most subtle debates. You can let them exist as open questions, resting at the edge of what is currently known. You can appreciate that very edge like a shoreline, where solid land meets an endless sea. It is enough simply to stand there for a while and listen to the waves of possibility coming and going. There is a special kindness in mystery. If everything were already known, if every pattern were already mapped, if every question had a final answer, there would be no room for exploration, no space for wonder, no reason to look up at the night sky and feel that quiet pull of curiosity. Mystery is not an enemy of understanding. It is the landscape in which understanding can grow, a blank page on which new insights can be written, a dark region into which light can expand. For most of your life, you move through the world with practical concerns. You think about tasks and plans and responsibilities. You navigate schedules, obligations, stories. There is value in that, but there is also value in moments like this, when you are allowed to zoom out, to see yourself not as a list of duties, but as a temporary pattern in a vast, informational cosmos, a pattern that can pause, take a breath, and notice that it is here at all. You may find comfort in the thought that you do not need final answers to live a full life. You do not need to know whether reality is ultimately digital or continuous, whether space-time is emergent or fundamental, whether consciousness can be written in equations, to feel that your experiences have weight within your own story. Meaning does not wait at the end of a solved theory. It arises in each moment when your inner patterns resonate with the world around you, with other minds, with memories and hopes and quiet joys. Think of your day as a sequence of exchanges, of information and energy. You sensed light and sound, you moved, you spoke, you remembered. You imagined, you changed the state of your brain and of the world in small ways. A word said, a gesture made, a message written. These changes spread through networks of other people and objects. Some of them will fade quickly, others will leave longer traces. All of them are part of how the universe continues to transform its own patterns from one moment to the next. Your life is woven into that process, not as a separate fragment, but as a continuous thread. If reality is deeply structured, then your search for structure is not out of place. If the universe is rich in patterns, then your sensitivity to pattern is a natural response to where you are and what you are made of. You are not an outsider trying to read a foreign code. You are one expression of that code, becoming self-aware, for a time, a self-referential pattern that can notice itself and its surroundings before it changes into something else. There can also be a gentle peace in remembering your scale. You inhabit a small region of a large planet orbiting a star, in one arm of a spiral galaxy. The galaxy is one among many in a cosmic web that stretches far beyond what you will ever see. And yet, within this small region, within this limited time, your experiences are complete. They fill your horizon. They are the entire universe. As it appears from your vantage point, the contrast between these scales can feel overwhelming, but it can also be soothing. The problems that feel heavy in the center of your attention are local. They are part of a much larger context that does not judge or hurry or demand. They are events in a vast and quiet flow. You do not need to solve reality, to rest inside it right now. All you need is to allow the mind's grip to loosen a little, to let concepts and arguments and frameworks sink into the background like ripples calming on a pond. What remains is the simple fact of being aware of sensations, of breaths, of the slow drift of thoughts and images. Awareness itself does not need a theory to function. It just is, a luminous, silent space in which patterns appear, change, and fade. If reality is information, then this moment is one configuration among many, a particular arrangement of signals in your brain, of signals in your body, of signals in the world. Outside your room, tomorrow, the configuration will be different. Different memories, different concerns, different sensations. But right now, there is only this slice of an ongoing process. You do not need to hold all of it. You can let it pass through you like a gentle current while you float, weightless, not trying to control every detail. There is a certain beauty in patterns that you never fully grasp. We map the stars, knowing we will not name every point of light. We study atoms, knowing that deeper layers may remain hidden. We explore consciousness, knowing that some aspects may always lie just beyond our conceptual reach. But this incompleteness is not a flaw, it is the open door through which future minds will step, continuing the work that earlier minds began. You are part of that chain, receiving ideas, transforming them, passing on new combinations. The story does not end with you, and that can be reassuring. As you drift towards sleep, you can imagine your thoughts slowing, their edges softening. The detailed questions of physics and philosophy can dissolve into simpler sensations: the weight of your body, the rhythm of your breathing, the feeling of lying in one small place on one small world, orbiting in a vast, calm darkness. You are held by gravity, by the atmosphere, by the long evolution that shaped your form, and by the countless patterns of information that sustain your life. From the beating of your heart to the firing of your neurons, all of it continues. Whether you attend to it or not, you are allowed to rest within that continuity. You exist in a universe that can question itself through you. You exist in a universe that can feel its own intricacy. As awe, you exist in a universe where patterns can become stories, where stories can become science, where science can circle back into quiet wonder. You exist at the crossing point of many kinds of information: physical, biological, cultural, personal. For now, you can let them all settle into stillness. Let the thought remain softly that you do not need to hold the entire cosmos in your mind. The cosmos is already holding you. You do not need to complete every pattern. Some can remain unfinished. Like constellations, half hidden by cloud, you do not need to close every question. Some can remain open, like doors in a peaceful corridor. Tonight, it is enough to lie here, to breathe, to feel that you are part of something vast and subtle and ongoing. Whether or not it is finally made of particles, of fields, or of information, it has made room for you within it, for this moment, for this rest, for this gentle, unhurried drifting into sleep.